we are discussing carbon structures, and we have already discussed by now structure of graphene, diamond and graphite. Today we will discuss, our topic is another carbon structure which is very important and is recently grown much importance in research and development, is the carbon nanotube. So, carbon nanotube, also sometimes abbreviated as CNT. So, what is carbon nanotube? The best description of carbon nanotube, and a simple description, comes from relating it to the structure of graphene, which we are already familiar. So, we have seen that graphene is a hexagonal structure, a single sheet, two dimensional hexagonal sheet of carbon atoms, just like one layer of graphite. So, carbon nanotube is nothing but a rolled up, it can be considered as a rolled up sheet of graphene. A tube made by into a tube graphene, a rolled up sheet into a tube. This structure was discovered in 1991 by a Japanese scientist, electron microscopist Sumio Iijima. Probably only one eye. So, Sumio Iijima in Japan discovered it in 1991. There is a lot of discussion in literature whether this was the first real first observation of nanotube, or some people have seen it before that. But the fact remains that only after his 1991 paper in a journal called Nature, a very famous journal, the topic actually caught the attention of the world, and a lot of research and development, it established itself as a field of in its own right. So, that credit does go to Iijima. So, let us try to relate it to the graphene sheet, we will do that soon. Let us look at some classification of carbon nanotube. One particular scheme of classification is the so called single walled nanotube or multi walled nanotube. So, let us say CNT, we are classifying it into SWNT or single walled nanotube, or MWNT, which is multi walled nanotube. Name itself is self explanatory. In a single walled nanotube, a single graphene sheet is rolled into a tube form. So, you have a single tube, and that is called a single walled nanotube. Multi walled nanotube has several walls, and again can be classified into two types depending on its structure. One is called, interestingly, the Russian doll structure, and another parchment structure. The Russian doll structure is several concentric. So, instead of just one graphene sheet rolled into a tube, you can have several graphene sheet multi walled. So, several concentric tubes, if they are there, then this is the Russian doll structure of a multi walled nanotube. In a parchment structure, actually there is a single graphene sheet, but that rolls itself like a parchment into a multi-walled tube. The distance, the intertube distance in the case of multi-walled tube is about 3.4 angstrom, which is same as the interlayer separation in graphite. Interlayer separation of graphite. So, you can think of it as a curved graphite instead of flat graphite. Another classification, so that was one classification scheme where we got the single walled and multi-walled nanotube. Another classification is based on what is called chirality. So, based on chirality, we again classify nanotubes as either chiral or achiral. Well, chiral is just another word for handed. So, when we say chiral, we mean that it has a handedness. So, it will come in two varieties, a right handed and a left handed version, whereas achiral will not be handed, it will not have these two varieties. So, for example, my hand, we know that our hands are left handed and right handed. I have a left hand and a right hand, and these cannot be superimposed, although they can be imagined to be mirror image of each other. So, but my single hand lacks any mirror symmetry. So, that is why when I reflect it into a mirror, a different handedness hand is produced. So, for chiral or handed structures, it is important that mirror plane is absent. So, mirror is absent. Only when mirror is absent, you can have left handed and right handed version of an object, and that is called a chiral object. Whereas achiral is not handed, in this case mirror will be present. Think of a sphere. You do not think of a left handed sphere or a right handed sphere, and this fact is related to the fact that a sphere has several mirrors. A cube does not have a left handed or a right handed version, because cube has mirror. So, any object which will have mirror will not have left handed or right handed version, whereas object where mirror is absent, it is possible to have both left handed and right handed. So, in science or in crystallography, the word chiral and achiral is used for that. So, when we say CNT, the carbon nanotube is chiral, we say that that nanotube will not have any mirror plane, whereas achiral nanotube will have mirror plane present. So, it is more symmetric, achiral is more symmetric. Again, in achiral, two different kinds of tubes have been identified. So, one is called the zigzag tube and another is called armchair tube. So, we will look at this soon, what is the meaning of zigzag and armchair. So, let us try to make a tube out of a graphene sheet. So, this is a model of a graphene sheet, just the hexagonal rings are drawn, and if I fold it into a tube, I will get a nanotube. To do this, and I want to make a zigzag tube and show it to you. So, let me try to fold this. So, all I am trying to do is to bring the two edges together such that they meet coherently without leaving any gaps or so. So, if I can do that, then I have a nice carbon nanotube. In this tube, if you see, so let me first try to paste this edge. So, Shrikant, can I take your help? So, Shrikant is a TA in my course and he will help me to paste it. So, sellotape is very important in carbon structure, as you know from discovery of graphene, which was sellotape played an important role. Now, it is playing an important role in making my model. Yeah. So, thank you Shrikant, he has pasted the tape and I have now a tube form. This tube is known as a zigzag tube. Why it is known as zigzag tube? That if you look at the free edge of the tube, then you see a zigzag structure. The top free edge is a zigzag structure. Of course, in real nanotubes, there will be a cap, a carbon cap of fullerene on the top and bottom to close the ends. So, the nanotubes are closed structure instead of open tubes, but still the fact remains that there is a zigzag structure on the top, and based on this a name zigzag is given. But this is not the only way to fold the tube. So, another tube I will fold in another structure known as the armchair structure. So, this is again the same hexagonal tiling with carbon structure shown. So, again I am starting with graphene, but now I want to fold it differently to make it an armchair tube. And one thing, so please see this, that in the, yeah, or maybe I can show it here. In the zigzag tube, along the tube one set of bonds is parallel to the tube axis, and you can see that if you draw a plane passing through these bonds, that will act like a mirror plane of the tube. So, a mirror plane is present in this tube also. So, if I can draw that mirror plane for you, maybe I can use a red pen and I am trying to draw a line representing the mirror plane. So, you can see that if you imagine a plane passing through this line and the tube axis, the two parts of the tube are mirror symmetric to each other. Also, there is another mirror plane and that is perpendicular to the tube axis. So, if I draw another line, let me use another color pen now. So, perpendicular to the tube axis, this plane which will cut the tube, a cylindrical tube in a circle. So, this plane also you can see that the top and bottom atom are mirror images of each other and all the atoms will reflect into each other. So, there is this zigzag tube has two mirrors and obviously, this will be achiral. The zigzag tube cannot be a left handed zigzag tube or a right handed zigzag tube, it will just be a zigzag tube, it is achiral. So, now let me try to make armchair for you. So, the same tube, this is what is interesting about nanotube structure, that although graphene is the same single structure and by folding the graphene or rolling up the graphene we are making the nanotube, but depending on which way we fold, we get different structures of the nanotube, and these different structures also have different properties. So, now I am trying to make an armchair for you. I will again need help of Srikanth. Yeah. See, I am trying to match the atoms. If I do not match the atom, then something like this will come. Yeah, something like this will come. So, your tube is not good, or is something like this if it happens. So, what I am doing when trying to make the tube is to bring and join the atoms coherently, such that there is no such boundary, and the tube is continuous along that line. So, we have synthesized another nanotube now. This is the armchair nanotube. Why it is called armchair? Again, if you see the top edge of the tube now, the last time if you remember, in the zigzag tube we saw a zigzag structure, but now you are seeing an interesting structure that there is a horizontal bond, then there is an inclined bond, another horizontal, then oppositely inclined bond, then horizontal bond. So, it is not going zigzag, it is doing something else, and this is what has been imagined by somebody as an armchair. So, these can be thought of as arms of the chair, and this is the seat of the chair, and somebody can sit comfortably. So, if I can show you here, yeah. So, you can see here like this. So, somebody can be sitting comfortably there with his hands on the two sides. So, that is why the name armchair has been given. So, we will look at these two tubes again in a slightly different and more mathematical way, and for that new notation, the NM notation of carbon nanotube is required. So, let us look at the NM notation, because in literature you will find a 10-10 carbon nanotube, a 10-10 tube, 10-10 CNT, or a 10-0 CNT, or 5-9 CNT. The question is, what is the meaning of this notation? So, this is what we want to explain. So, the NM notation we will explain. We will also define two important concepts which are related, the chiral vector of the tube and the chiral angle. So, to do this, we again begin with our graphene sheet, and now I will try to show carefully what I was telling you, that what I do when I was trying to match the atoms along the tube axis. So, let us look at this graphene sheet. When discussing the graphene structure, we have already talked about that in the graphene structure, it is the alternate atoms. It is the alternate atom. So, if I take this atom as in my origin, then the near neighbor is not equivalent. Let me use slightly brighter color maybe. So, if this is my origin, then the near neighbor is not lattice equivalent, because it has a different kind of neighborhood. You can see this, if I take this as my origin OO, then the origin atom at the origin has a neighbor on its right at a distance equal to the carbon carbon bond distance d. But this atom at the same distance, if I travel d, we come into the center of the hexagon, and there is no atom at the center of the hexagon. So, this we had explained while discussing graphene also. So, I am repeating this here. So, alternate nearby atoms, near neighbors are not equivalent in the lattice sense. It is the next near neighbor which are equivalent. So, I leave one set of atoms and try to mark all the equivalent, crystallographically equivalent or lattice equivalent atoms on this sheet. So, then I keep taking the alternate ones, leaving out the near neighbors. So, all these carbon atoms which I am now marking are equivalent to each other, translationally equivalent to each other and equivalent to the atom marked as the origin. And the ones I am leaving out are not equivalent to this set, because there is no lattice translation in the graphene sheet which will bring the marked atom to the unmarked one. So, essentially these red marked atoms are now forming the lattice of the graphene. In this lattice, we need to find two vectors which are the basis vectors, and that is selected. So, I for basis vector I have to go from the origin to the nearby equivalent atom. So, I cannot go to the nearest atom, I go to the next nearest atom and I mark this as one of my basis vectors. Let me call that vector A1, and then another vector let me call that vector A2. So, these two green vectors which are at an angle 60 degree to each other define a primitive unit cell of graphene. So, if I complete this rhombus will be a 2-dimensional primitive unit cell of graphene. So, these two vectors are used to then define all vectors, all lattice vectors in this graphene sheet. We are trying in this exercise, we are trying to explain the NM notation. Now, you can see that when I was trying to roll a sheet, I was trying to bring the atoms together such that there is a coherence between them and there is no defect along the axis of the tube. So, the atoms should match. In terms of lattice, that essentially means that I can fold the graphene sheet in a way such that any of the lattice equivalent atom is identified with the origin. So, if I fold in such a way that a lattice equivalent atom, any of these lattice equivalent atom, if it overlaps the origin, I get a carbon nanotube. So, this brings us to the fact that if I take any vector in the graphene sheet. So, let me take this particular vector. This blue vector. So, this end atom will be identified with the origin. So, that is how I will wrap. So, I will wrap such that I bring the head of this vector to its tail at the origin. So, I will get a tube. So, you can see the vector which I have drawn here, the blue vector, will become the circumference of the rolled up nanotube. Such vector are known as the chiral vector of the tube. Chiral vector. A more transparent name could have been, so let us use that, is a circumferential vector. because this is the vector which will become circumference of the tube. Obviously, a vector normal to the tube to circumferential vector, for example, a vector like this, let me call that T, will form the axis of the tube. So, this tube will be folded like this, circumferential vector becomes the circumference and the vector along the vector perpendicular to the chiral vector. So, the chiral vector becomes the circumference of the tube and vector perpendicular to the chiral vector becomes the axis of the tube. So, that is the definition of the chiral vector, and a chiral vector will always be a lattice vector in the graphene sheet, otherwise you will have defect along the line where you will join, as I had shown you in my previous example in trying to when I was folding the nanotube. So, chiral vector has to be, so chiral vector, let us call this C, and this chiral vector C has to be a lattice vector of graphene, which means it can be expressed as linear combination of the two basis vectors A1 and A2. In particular, you can see that the chiral vector which I have drawn here, this particular chiral vector is 4 times A2 and 0 times A1. So, sorry, I should write first the A1. So, 0 A1 plus 4 A2. So, I can call this a 0 4, the nanotube which will form will be given the designation a 0 4 nanotube, which means 0 4 is the lattice vector of the graphene sheet which will become circumference of the nanotube. So, C has to be a lattice vector of the graphene sheet. So, C can always be expressed as n times A1 plus m times A2. Any lattice vector, as you know, since we have selected a primitive unit cell and A1 and A2 are the basis of the primitive vector. So, any vector in this sheet will can always be expressed as n times A1 plus m times A2. So, the resulting tube will be called an NM tube. So, I hope this designation or this notation is clear. So, we have, so you can see that if one of the components is 0, so 0 4 tube, this time we are getting a zigzag tube, because you can see the zigzag structure along the circumference. If you want a armchair tube, you will take a different chiral vector and it will have a different NM designation. So, let us now try to make a chiral vector for armchair tube. So, I again mark all the alternate atoms as my equivalent sites, and in this graphene sheet I will identify a vector which when wrapped up will become circumference of an armchair tube. So, remember that armchair had a armchair along its edge had something like this. So, which means that the lattice vector or the chiral vector for the armchair tube will be something like this, what I have shown in black here. And if I take my basis vectors again, two vectors at 60 degree, this time I have changed the orientation from, but that is allowed, you can take them in any orientation. So, if this is my A1, this is my A2, you can see that this chiral vector which I have now marked will be 1 A1 plus 1 A2, then 2 A1 plus 2 A2, 3 A1 plus 3 A2. So, the one which I have drawn out is 3 A1 plus 3 A2 in terms of these A1 A2 vectors. So, which means the resulting tube will be a 3 3 tube. Now, I will fold like this to bring the head of this vector, the chiral vector, to its origin, and if I join, then I will get a tube which will be a 3 3 tube. So, in general, any NN tube will be an armchair tube. So, if the two components are equal, then you will have an armchair tube. Finally, I will show you. So, both armchair and zigzag, as you know, were chiral, but of course, since all these atoms are equivalent, any of these atoms could have been brought to the origin and a tube could have been created. So, if you now see, let us randomly make let us randomly choose one, let us choose this atom, and let us say that we want to identify this atom with the origin and create a tube, which means my circumferential vector will be going from origin to my chosen atom. Now, if I try to define this in terms of N and M, we see that we have to go, remember A1, and then we took A2, then another A1, then another A2 to come to this point. So, this point was 2 2, because we had taken 2 A1s and 2 A2 to reach here, and after that I will I want to reach here. So, sorry, this is not parallel to that. So, I should go parallel to this direction. So, which is this one, I had overshot. So, this is a line which is parallel to my A2. So, I should come only up to this much. So, not 2 2, but to 1 1. So, here I have already come to 1 1, and then I keep going in the 2 direction by 1 2 and 3 steps, 1 2 and 3 steps. So, 3 extra steps in the 2 direction, which means this location is a 1 4 location. This vector which I have drawn as my chiral vector C is 1 times A1 and 4 times A2. You can see now here clearly from this triangle that I go 1 times A1 and 4 times A2 to reach there. And so, this becomes my circumferential vector, and if I now wrap it up, then this will be called a 1,4 nanotube, and this will be a chiral nanotube. Armchair and zigzag were achiral, this will be a chiral nanotube. So, in summary, in NM notation, if one of the component is 0, N 0, so this will be zigzag. If both are equal, Nn, then we have armchair. And if neither is 0 nor they are equal, we have Nm, then you have a chiral tube. So, just one more concept which I wanted to show you is the chirality angle or the chiral angle. Sometimes the tubes are characterized by what are called the chiral angle. So, that is nothing but the angle which the chiral vector makes with one of the axis, usually taken to be the first axis A1. So, if we let us say if we have, if this is my origin again and these are my basis vectors, and let us say that this is the chiral vector C, then this chiral vector is making an angle theta with A1. So, angle of the chiral vector with A1 will be known as the chiral angle. Angle of chiral vector C with A1. That is the chiral angle. And in fact, you can try to derive, I leave this, I do not do this now in this lecture, but I leave it as an exercise that both the diameter D and the chiral angle theta of an NM CNT can be expressed in terms of N and M. And of course, for D you also require a length parameter, which is the carbon-carbon bond length. for D. So, this is a interesting geometrical exercise which I want to leave it as an homework for you, because you can see that once the circumferential vector Nm defines the circumferential vector C, because C is nothing but n times A1 plus m times A2. And of course, once you know the vector C, the length we are telling that C becomes the circumferential vector. So, length of C is nothing but circumference So, this will become pi d. So, with this relationship you can find the diameter in terms of n and m. An angle between C theta is by definition angle between C and A1. So, it is a nice exercise in vector geometry in non-Cartesian frame, because your two A1, A2 are not at 90 degree, but at 60 degree. So, I leave this as an homework exercise for you. So, thank you. With this we finish our discussion on nanotube. We are coming close to the end of discussion on carbon structure. Maybe in the next video we will discuss little bit about fullerene.